Okay, good afternoon, everybody. My name is Rudy Shankar. I'm the director of the Energy Systems Program, and welcome to our spring project symposium. This is a semester ending symposium that we host, and is basically to showcase, in this particular case in spring, we do the end of a 6 credit project that students complete, so you get a chance to hear from them. And we've, of course, completed an entire year where we worked under a pandemic situation, which means all the meetings and the projects themselves were conducted virtually and remotely. And it's nothing new for you guys too. So we have a shared experience that we have learned a lot. We can learn a lot from each other. I will be sharing some of that during this presentation, and I'd like to hear from you guys about some of the things that you have had to adapt to. There's no doubt that this has been disruptive, and we need to adjust to these disruptive conditions. And so, if we've kind of fallen behind in certain things, I apologize, but I believe we have actually gained quite a number of things through this kind of interaction. But I just want to kind of, before I get off that subject, the biggest burden has been on the students. It is students come to campus, and for them to not be able to socialize as much as they were used to, has a lot of different dimensions. But I really have to thank the students for, you know, changing to the new environment and doing really well, excelling in it. This project it's called a capstone project. It's a 6 credit course out of 30 credits that they have to earn to get a Master of Engineering in Energy degree. So this is very central. It's not only 20% of all the credits, but for each hour of credit during the week, the students are expected to put in 5 to 10 hours of off-class work. So if you do the math, over 2 semesters, they spend anywhere from 500 to 1,000 hours on this capstone project. So when we say it's an industry-sponsored capstone project, we're not too far from what industry you guys expect, and that is results. And so we have a well-defined scope of work that industry project managers are briefed on every week or 2 weeks, depending upon the practice that's been set up between the student and the industry project manager. What I'm saying in so many words is it's a big deal. It's a big deal for the students to go through something like this. They are the grades are based on several attributes. Innovation is one of them. Discipline, being able to document, being able to collaborate. Some of the things that they see and will see in real life, are some of the features that we're looking for as far as the project deliverables are concerned. So one of the deliverables is this presentation, and the other is a final report, which is comprehensive enough to kind of basically explain everything they've gone through. Okay. Now, this is the first, can't advance this here. There we go. Good. So, progress during a pandemic. It hasn't been easy to us and to you too. And, some of the things that we had to deal with, as the situations arose, especially for the capstone projects. One of the other features was not only to kind of brief me, the director, on progress, but also to meet with you in the industry project managers, and again, collaborating with the industry project managers and putting this together. They had to adjust, they had to adapt, and when we look back over the time, would we have guessed that we would be where we are today? I don't think so. Some of the things that have occurred has made it possible where we can look forward to coming back to something close to normal. I think definitely in the fall, we'll have a hybrid situation, some in class and some in person and some remote. But anyway, it's great to be where we are today, and hopefully things will get even better as we go forward. But as I said before, I think we've learned a lot, and obviously you guys have gone through the same thing. You guys have learned a lot, and there's something we could be sharing as we go forward. The other thing that I wanted to point out is the nature, the profile of a typical student that comes into this program has changed. We are getting not just full-time students, but a number of part-time students. In fact, the number of part-time students has been the greatest ever. I've never had so many part-time students. And so they don't part-time students don't complete the program in 10 months. For them, it takes 3 years. So you'll be seeing fewer projects presented at a symposium like this, just because of the nature of the students who come through this program. In this particular case, typically we have like 4 to 6 projects that are completed, that are presented. This year we'll have 2. And next year we may have more than 2, we may have 3 or 4. So it's kind of the consequence of having part-time students, which is, in a way, it is good. Because we're getting diversity in students, not only people who have just plain academic background, but they also have industry background. So that adds to the mix of students who can interact in the classroom. So just go through the agenda briefly. You've gotten handouts mailed by Susan. For the first couple of hours, we'll go through this project presentation, and then we will have you complete evaluation of the projects. It's a semester custom that we have adopted, sorry, where we want you to basically give your opinion on, what's your impression of what you heard about the project, for 4 of the 8 attributes that we utilize to be able to assess how well the student did. From 1:45 to 2:30, I've invited Clint Carter, who's the director of the Performance Operations Center at Luminant Energy. Clint is a longtime colleague of mine, and he'll be giving a keynote address which will last till 2:30. And after 2:30, we'll be going into our traditional industry advisory council meeting. Basically, it's a progress report of what the program has gone through, and get your ideas and interactions and what we could do better as we go forward. So it's pretty a full program. And since we're operating in a virtual remote situation, things probably will go wrong. People will be cut off, but we've gone through this. In fact, the most common phrase, there's so many phrases that we have when we go through a Zoom meeting. Please unmute yourself is one of those famous things, even in very well-respected speakers see on TV, they forget to unmute or mute themselves. So one request I will make is, I request that if you're not speaking, please mute yourself. And when you have a question, of course, you have to unmute yourself. So it's, please, we'll go through that. So before we start, just want to kind of thank the students who will be graduating. As I said before, these are the full-time students who joined, Dylan, Ammerman, Jasper, Chamba, who were part of Team 1, and Thomas Agate, who was part of Team 2. And you can see the title of their projects, and it is so, gosh, somebody should learn to spell virtual. apologize for the spelling mistake. um, um, so these two projects in many ways capsulizes some of the challenges we're going through. The virtual power plant is a project that really had its start three cohorts ago, 3 years ago at Lehigh. It's been built to this point, where it's culminated in a very interesting proposition is how can you harness the capabilities of distributed resources to be able to provide peak demand or be able to have demand response. Basically the words are very fitting. It's a power plant that's formed by taking individual assets and using artificial intelligence and machine learning. So Jasper and Dylan will be talking about this project. Well, our project sponsor is Dernet Soft, which is backed by OSI Soft, which has recently been acquired by a bigger company called Aviva. But thank you again for all the industry partners in that project. So they will start off first. The second project would be dealing with the supply side, especially looking at nuclear power as a in the clean energy system. How could it in the decarbonization effort is not just for the supply side that the virtual power plant that would be addressing, but also on the demand side, that is fossil intensive fuels are used in several industrial processes. And Thomas Agate is going to talk about what's the feasibility of nuclear energy being able to substitute fossil-based fuels. Again, the project sponsor is EPRI, Tina Taylor. And thank you, Tina, for guiding us through this. I think we got some exciting results to share with you guys. So again, the virtual power plant will be presented first, and then nuclear power and a clean energy system will be presented second. And so I'm going to share the screen with with Jasper and Dylan. Okay, so Susan, I go to participants, right? Susan, I think you need to.
Oh yeah, Rudy, you need me to make them host and yeah, hold on a second. Co-host. All right.
Yeah, you need to do that. I think I can't do it mine.
Yeah, there's Dylan and Jasper. Okay, you're both co-hosts now.
All right, and so if others could mute themselves, and so Dylan, Dylan and Jasper, please get on. You can get on.
There we go. Can everyone see?
Yep.
So I'm Dylan, and my partner Jasper's here, and we are part of the Intelligent Virtual Power Plant Group, sponsored by DER NetSoft. A few acknowledgements before we get started. Of course, to DER NetSoft and OC Soft, to the Institute of Electrical and Electronics Engineers, the Smart Inverter Working Group, the California Public Utility Commission, the Federal Energy Regulatory Commission, the EPRI, the Electric Power Research Institute, the National Renewable Energy Lab, and former Lehigh University ESE and DER NetSoft capstone project groups. So a quick rundown, everything we're going to be going over today. We have the project history and the project scope, DER and VPP definitions, what exactly they are. We'll go over the virtual power plant communication links, the smart inverter requirements to be a part of this virtual power plant, the ISO/DSO request side data models, the DER asset data, and finally the DER response side program. So this project has been in the works for many, many years, kind of leading up to it. So back in 2017 and 2018, DER NetSoft partnered with Lehigh to create a PV solar favorability rating index. And then in 2018, they added onto that the previous work, adding storage systems to that rating index. In 2019 and 20, they added EVs and charging stations to that rating index way back. And then this year, Jasper and I, with our project, we took a little bit of a pivot to the virtual power plant, the DER program design. So here's a quick explanation of kind of what it is. This is, you can see things in red here is the scope of our project. Basically, an ISO or will send a utility a request. The utility will send DER NetSoft a request for some sort of service, whether it's load curtailment, we'll go over demand response, or demand fulfillment, typical day ahead, things like that. The program will select a number of DERs in DER NetSoft's database to respond to that request, and it'll use our program as well as AI to select the best assets to respond, and then they will respond and then get penalized or rewarded accordingly. Project scope. So last semester was a lot of research. We researched existing VPP programs. We researched the utility approach to DERs, how they're handled, and the communication links between them. And then we collected data / requirements for DER aggregator program design, exactly everything that needs to go into creating this program. So this semester, Jasper and I kind of broke up a little bit. I researched and decided on data models for request and response side. I took the request side, the ISO, DSO side, and Jasper took the DER side, the response side. We created a program that accepts and responds to grid requests based on the data models that we created. And then we're currently working on testing and improving that program based on simulated and real data that we have from DER NetSoft. So what is a DER? DER stands for Distributed Energy Resource. It's typically located behind the meter. They're private assets that people may own themselves. And examples of DERs, there's generation technologies like PV solar, wind, things like that. There's storage technologies like batteries, things like that. There's dispatchable loads, such as generators, fuel cells. And there's load curtailment. We'll get into demand response a little bit later. Load curtailment opportunities. And they're all considered DERs. What's a VPP? It stands for Virtual Power Plant, and it's a cloud-based digital network of intelligently collaborative assets. And that's, so basically you could think of it as in opposition to a brick and mortar power plant. This is a digital collaboration aggregation of energy assets, all working together intelligently. It widens the energy market and increases grid stability, resiliency, and reliability. And it can provide and improve ancillary services. So here's a little cartoon of exactly how it might work. So an ISO would notify utility of demand. The utility would then notify DER NetSoft with a specific request for a service. DER NetSoft is the aggregator. It aggregates together several different meters, which we'll go over smart meter requirements later. And then behind those meters, private assets might own batteries or some sort of generation technology or some kind of dispatchable load. And then DER NetSoft selects the best assets to respond to the request. Some benefits of integrated DERs and virtual power plant. It supports the grid by providing ancillary services such as frequency and voltage control. It gives increased resource and operational flexibility, to talk about a little bit more with demand response. And that gives the opportunity for load shifting and peak shaving, things along that nature. And it gives the bigger picture here is increased greener options for power. So that reduces greenhouse gas emissions, which is important today. And what opened the door, this order here, FERC order 2222, it really opened the door for a project like this to even exist, or the concept of a virtual power plant to exist. It opens the door, this FERC order opened the door for DERs to participate in the wholesale market by removing barriers to entry. So before FERC order 222, you had to meet a minimum of 1 megawatt capacity to be allowed to participate in the wholesale market. But with this order, they now allow an aggregator to aggregate several smaller capacity assets together. So now to meet that minimum capacity requirement. And that was signed September 2020. So this is a brand new thing. And then with this law, their DERs are projected to grow from supplying 65 gigawatts to 380 gigawatts of energy to the grid in the next 4 years. And you can see down below the breakdown of exactly how that will go. And with this, I'm going to turn it over to Jasper to talk about the virtual power plant communication links.
Thank you, Dylan. So for virtual power plants to be effective and operational, you need both the physical and communication links. But for DERs to be connected to the grid, they already have the physical interconnection through net metering. To ensure the success of virtual power plant, then we need to look more into the communication links. That's how all these distributed assets will communicate to one central point and using their resources, be able to respond to the grid request. So to further talk about communication, we looked into smart inverters, which are the main points of communication between the DER assets and the virtual power plant. And in California, they were among the first states to require implementation of smart inverters. And these requirements were prescribed in what now we call Rule 21. And the smart inverters will have specific communication, technical communication and technical specification. And those are outlined in 3 phases. And we'll go through each of the 3 phases briefly. So the first phase shows the capability to perform 7 autonomous grid functions. And those functions, I just mentioned them here. They are voltage write-through, frequency write-through, soft start reconnection, ramp rate controls, fixed power factors, dynamic volt VAR management, and anti-islanding capabilities. So these are some of the grid ancillary services that DERs can provide autonomously as long as they're connected through a smart inverter. And on the second phase, this is where the communication requirements for the inverter are outlined. And the main takeaway from this is IEEE 2030.5 is the default protocol that was chosen to be used for this type of communications between individual DERs with an aggregator and to the utility, or directly from individual DER to the utility gateway. So the protocol must be supported by individual DER systems. And as you can see, maybe you have a rooftop solar, you have to have a smart inverter that can communicate using this protocol. If you're a facility, you need to have, if you have an energy management system, it has to support this communication system or protocol. If you're an aggregator, you have to be able to communicate this. And similarly, if you're a utility, you need to be able to support this communication protocol in order to effect the communication between the different aspects of aggregation and virtual power plants. And on the third phase, they're adding additional advanced inverter functions. And this must be done by Smart Inverter Working Group in California. So they keep trying to see what might be necessary for these smart inverters and what is possible. And the functions that have been put into effect by now in this third phase include data monitoring, remote connection and disconnection of the smart inverter, maximum power controls, frequency watt and volt watts, scheduled power values and models. And these all additional to the first phase. These are also done autonomously by the inverter. So I'll give it back to Dylan to talk about ISO DSO request side. Dylan, you're muted.
Yeah, you're still muted.
That's embarrassing. So at this point, Jasper and I split up and I took the ISO DSO request side data models. I researched existing typical request types of existing ISOs, and we're currently DR net sauce in the California market. So it was with the California ISO, as well as their utilities like PG&E, San Diego Gas and Electric. And we specifically look for requests that are in services that our small virtual power plant could respond to. So DR NetSoft gave us a subset of their assets that they have under contract, and we use that for to create our program. And at this point, it was important not to lose sight of the big picture, because it's not a single asset responding to a request from the utility, but it's a group of assets aggregated together, all contributing to fulfill demand. So with that, we were able to come up with 3 general request types. And the first one being dispatch, and that's your typical day ahead demand fulfillment for energy. The next is operating reserve, and that's a reserve that's dispatchable for black start reconnection, ramp, and emergency backup in emergency situations. And finally, we have the main thing our program is based on is demand response and low curtailment programs. So that's the ability for an asset or a group of assets, in our case, to reduce load over a designated period to reduce peak demand and the need for additional generation on the utility side. So here are the request side data models we created. So if a request were to come from utility, it would have the request ID, the utility that's sending the utility ID, and the request type. And then depending on request type, it'll also include a number of other factors. So for low curtailment, it would have the NAID that's looking to low curtail for there, the quantity, the date time, the duration of low curtailment, and it could either be one time or reoccurrent over several weeks or months. For dispatch, it's just quantity, date time, and duration. And then for operating reserve is the same. It's quantity, date time, and the duration the reserve would need to be available. So our program's mainly based on demand response. So the way demand response works is the ISO would notify the utility to reduce load. The utility then sends a request to the virtual power plant, and the virtual power plant responds by reducing load among its eligible DER assets. And buildings can reduce load either by reducing demand or by reducing energy consumption, or by increasing their own generation through DERs to offset that demand. Demand response can be one time, or it can be scheduled to be reoccurring over a period of time. And normally they have curtailment events over times of high demand, normally the summer. And DERs are incentivized to participate in demand response through time of use pricing. So in this case, during high peak hours, the price of electricity is going to be extremely high, so they would want to reduce or use their own energy if possible through critical peak pricing, variable peak pricing, and critical peak rebates. And then also something to consider is DERs would rather consume the energy they generated than sell it off at the wholesale price and then buy energy at the retail price. They'd be taking a loss on that energy, or it'd be misvalued for them. So they would rather consume their own energy than sell it off at the wholesale price. So we looked at 2 types of demand response programs. The first being a base interruptible program. And this is a demand response program PG&E offers to eligible consumers. So it's they do it in targeted locations to avoid overloaded lines in times of high demand, normally during the summer months in California. Customers are given 30 minutes to 1 day notice to reduce load to the building's firm service level, or FSL. And that firm service level is adjustable, but it cannot exceed 85% of the building's peak usage the prior year. So when you sign up for this BIP program, the minimum you can reduce is 15% of your demand, but you can go lower as well. It's a maximum of 1 event per day and 6 hours per event. So 6 hours a day is the most that's the longest program or event they'll have. And it's a maximum of 10 events per month or 180 hours per year. So with that in mind, I have an example. We ran a quick example here with Santa Rosa Hospital. So in 2019, Santa Rosa Hospital's peak load was 2,163 kilowatts, and that was in August, I believe. So if you take, if they were to only reduce by 15%, their firm service level would be at 1,839 kilowatts. So that's what they set the firm service level at. Customers are penalized at $6 per kilowatt hour for going over that firm service level during a curtailment event. So if you were to commit to being a part of this demand response program during a curtailment event, you get penalized for going over your firm service level. And then using the table on the right and the usage data that DER NetSoft sent us, I was able to calculate the potential load reduction each month, and then the rebate they would receive each month for that. So in April, the potential load reduction was 5.6 kilowatts. If you multiply that by the $8 per kilowatt, because it's below 500 kilowatts, they would get rebated $45 at the end of the month, and billing is monthly for these rebates. In May, they would have saved $1,070, June $403, July $728, August $674, September $1,066, October $568. So it gives a total time rebate of $4,554. And that seems a little small, but it's important to remember that that's the minimum reduction. This is calculated using the minimum reduction, and it also doesn't take into consideration the amount of energy they're saving through reducing their peak demand and through reducing, their complete usage in kilowatt hours per month. So, and if that were to be factored in, savings would be much, much higher. The other type of demand response program we looked at was the capacity bidding program. And the way the capacity bidding program differs from the other program is this one's organized by an aggregator like DER NetSoft. So this one only runs through summer, so May through November, typically when most demand response programs run. It's day ahead. They'll be notified a day ahead of a curtailment event. And aggregators, the biggest difference between this one and the other one is the aggregator is in charge of marketing, customer acquisition and retention, support and notification. And the aggregators must get approved by PG&E to qualify for this type of demand response program. So basically, the utility kind of pushes all the heavy lifting on the aggregator, and they're in charge of getting customers and notifying of them when a curtailment event would be in place. So how they make money, the capacity payment is the California Public Utility Commission's approved price for an aggregator's commitment to participate in curtailment events. So I believe they get like a base rebate or a credit for being committed to being a part of this program. And the energy payment is what PG&E makes the aggregator for a curtailment event. So if there were to be a curtailment event that month, if they were to predict there would be an emergency and they would need to reduce demand, then that energy payment is what PG&E pays the aggregator for that. If there's no monthly event, the energy payment is zero, of course. Aggregators pay incentives to customers based on individual contracts that they set up with DR owners. So the utility pays the aggregator, DR NetSoft, and then they would pass on the incentives to their customers based on who participates and the amount. And non-compliance penalties are charged to the aggregator if they're not able to meet the demand they're not able to meet the reductions that they committed to. And then with all this together, just kind of to sum it up, we looked at local virtual power plant demand response opportunities in our market here in PPL territory. So in doing a little research in the summer of 2018, PPL hosted an event called PY10, which is an opt-in demand response program in which 24 customers over 60 facilities participated in at least one curtailment event during the summer. So in that summer of 2018, there were 6, they call them Act 129 events, but they're just low curtailment events. It resulted in 111 megawatts of power saved, reduced, and 1.88 million in incentives dished out to those 24 customers that participated. And so bringing it all back home here, hospitals, retail stores, warehouses, colleges like Lehigh, industrial plants, they could all aggregate buildings together into a virtual power plant, perhaps in the future, to participate in demand response. With that, I'll turn it back over to Jasper to take over the response side.
Thank you, Dylan. So with the DSO sending requests, we need to see how the response side will take the request and fulfill fulfill it. So we need the facility name. For our case, this is what we have. We have facility name, we have location, and we have the contract on the percent that each of the facilities are willing to reduce. We also have export and import data. We have a DER generation type. If they have a fuel cell, a PV, or combined heat and power, we have that information on the assets that we worked with. So typically, you will need to know the response type, response capacity. You need to know the time. You need to know the duration, and you need to know the location of the assets, because you need to respond within, say, an electric utility's boundaries. And with that, we use the data that was provided to do our analysis. So with our analysis, as I'll discuss in the next slides, we made a few assumptions. One is some percentage of the predicted generation, because you will use predicted data, because this is almost like day ahead market, or like it's a couple intraday, 2 hours ahead. So you need to kind of predict what will generate at that time. So we are assuming that a certain percent of the generation is committed to wholesale market, and that's the case if it surpasses what you are able to use or consume on a retail market. And the remainder percentage is used as a negative load, or is actually used to reduce the load for the facility. And as Dylan mentioned, this is the most preferred way. If you can use most of your generation to reduce your load, then it's more financially rewarding. So facilities have committed to demand response, and contracts reflect agreed net load reduction or curtailment percentage. And this is to say that for the data that DNetSoft gave us, we assume that they have already contracts with these facilities to reduce a certain amount of load in percents over the summer periods when most of the DER demand response programs are operational. So with that, I show an example of 5 sites here. So these are DER site IDs 1 to 5, and these DERs have generation. So the generators, some of them do have generation. So some of them, if they generate more than they consume, they will export some of the power. And if they don't, they have to import some of the power to make up for the load. And so we took generation, export and import data, and we use that to find the site load for each of the individual sites. And we made the assumption that these are the percentage reduction that these sites have agreed to. So 15% for the first 2 sites, 10%, 12%, 7%. Those are pre-agreed contracts. And based on that, we'll find the load reduced. So you take 15% of 1,000, for example, in the first site, you'll get 150 kilowatts at any time, at specific time instance. They're able to reduce 150 kilowatts. And because they are also generating 1,100, and we are assuming that we're only using 1,000 in the retail market, then the total offset in the retail market is 1,150, so 1,150 kilowatts. But the remainder 100 kilowatts that they generate, we assume that it's being exported to the wholesale market, and they're being compensated at the wholesale price. And as we say, they would prefer to be compensated at the retail price, but there are limitations to what you can inject into the retail market. So we're assuming here that's 1,000. So with all that, we were able to find the amount of load that each facility can reduce. And we use that data to run our program and to select the best assets in the next couple slides. So this is just to show the example of how we receive the data. So we have the facility names. So we use 5 facilities, as you can see on the very top. All those sites that have the IDs, we know the location, and this location ID could be an actual address. We could convert this to longitude, latitude data. You have usage points, which might not be so necessary in our program, but more so we have our assumed percent load reduction. So we need to know how much those facilities are willing to reduce. And for a time instant, let's say for 1 hour, let's say 7 a.m., you would find out how much they're willing to reduce at that specific time. So this will be basically what the program will be looking into. It will be looking into what they're willing to reduce at the specific time of request. So to just recap, contracts stipulate what time span and what % of the facility can curtail or offset the load. Most of the California demand response program are between 8 a.m. and 5 p.m. And as Dylan said, they're mostly in the summer. Based on requested amount, the designer program will choose the best assets to respond. And we'll show that in the coming slides. So this is just to show a larger data set after the calculations of what they can curtail at every specific 1 hour. And we just assume that they will curtail their % that they agreed at every specific hour, but this could be just reduced to the, depending on the contract, if they're only willing to curtail between 8 a.m. and 5 p.m., then that should reflect in this data. But our assumption here is they can curtail the load at any time. And as you can see here, this data represents what they are willing to curtail. And on the far right, that's the sum total of each hour, what they're willing to curtail at each hour. So that's basically what the virtual power plant will have as its capacity. And this is the data that I use for the program. But before I show you the results for the program that we ran, I'll just like to kind of go through how the program works on a bigger picture level. So first of all, you receive the DSO request. That's from the Dylan side, as is discussed. It will have utility ID, program ID, requested capacity, date, start time, duration. Once you receive that, you want to check available or predicted capacity. You want to see whatever the request is will be available when you need it, like the next day, if it's day ahead. And if it's available, you want to notify those specific DER assets that they need to respond to that request the next day or whatever time the request is for. And if it's not available, you need to notify the DSO that the capacity that they requested is not available. And the DSO can try to find other ways of making up for that power, but you need to notify them and continue using the assets that will be available. So once you notify the DSO, you move to selecting the best assets to respond. And that's just sending a notification to see to these assets, because this is day ahead market. And once they receive the notification, they will check whether the available capacity is greater than requested capacity. It will use all combination. If the available capacity is equal to the requested capacity, it will use all the assets. If the available capacity is less than requested capacity, it will also use all the that capacity, because it doesn't even meet the minimum yet, so it will have to dispatch all of it. So the way it selects the best combination right now, we're using the first set here, that's capacity. So I'm just running the program to select if the requested load capacity is 500 kilowatts. I will just run the program to select the best assets to add up to 500. But in the future, we want to have a feedback mechanism where the various DER participants are ranked depending on how they perform in the past or with other aspects, and we can use this as another means to decide on which assets are the best to respond instead of just using capacity. And also, I think the previous classes had done other ranking mechanism based on location, strategic advantages. For example, electric vehicle charging stations will have some locational advantage. So all those could be built into an artificial intelligence or some sort of machine learning to have more attributes other than capacity to select the best assets. So once you request these assets to respond, you'll have to wait until that specific time. For example, if you send a notification to a facility to curtail load, you'll have to wait. If it's day ahead market, you have to wait for 24 hours. If it's intraday program, you wait 1 or 2 hours, and then you have to track the response. You have to see how they respond. So you want to see if those if they responded well. You want to reward them. Maybe you have a ranking score or some sort. And if they didn't respond as expected, you want to penalize them. So if they didn't curtail the load as they had agreed in the contract, maybe the contract stipulates a way you can penalize them. So you want to follow through with some sort of feedback mechanism. So that's basically how we ran the program in Python. And we basically requested inputs manually. And as you see here, I inputted 400 kilowatts starting 1 p.m. for 2 hours. So I'm requesting a capacity of 400 kilowatts for 2 hours starting 1 p.m. So it will be 1 p.m. to 2 p.m. and 2 p.m. to 3 p.m. And the date here is just, we're using past data here, but this will be predicted data in real life. And after running that, that program, this will be, for example, the output console. You will see that specific date at the specific time you requested. That's the available capacity, 629 kilowatts. And the capacity, the program will tell you the capacity is available. So it will select the best assets based on what's available. And the sum combination of the best assets is 401, which this could be reduced to match exactly that. You could find the percent of the last asset, for example. So you can reduce the extra kilowatts, but this is close enough. And it will tell you where those best combinations are from. It will tell you the name of the utility that curtailed or that was selected to respond. And with that, you can follow up and reward and penalize depending on how they respond. So basically, it will show, it will respond accordingly. So you can see 1 p.m. here and 2 p.m. at the bottom. So it will respond depending on how much assets are there. It will select the best assets to respond at that specific time. And I ran in the next slide. So I ran for each of the sites, the 5 sites. I ran for 5 days. I ran the program for 5 days, 10 hours a day. So that's 250 data points for each of the capacity. And I want to see how many times this program will be able to fulfill the request. How much, in general, how much can we assume that this virtual power plant is able to respond? And as you can see on the graph here, until 500 kilowatts, it responds to it 100% of the time. So this virtual power plant can operate almost like a base generator at 500 kilowatts. So you almost guarantee that every time you request 500 kilowatts from this virtual power plant, you will have that fulfillment. But starting from 600, it starts to respond it's only able to fulfill 50% of the time. And at 700, it's only 2%. At 800, it's not able to respond at all. It doesn't have the capacity at that level. So with more sophisticated programming and use of machine learning, you can have some confidence level on how well these programs can respond, and it can operate pretty well at a certain level of capacity, because you know how much these buildings can curtail, you know how much generation you can have. So based on a lot of historical data and some sort of machine learning, you can schedule and plan for this with some sort of confidence. On the summary side, we know that these programs are implementable. You can have a better service selection. You can build in feedback loops, and you can use other forms of ranking mechanisms. And the main takeaways here is that the more the selection criteria, the better. As I said, for this program, we only used capacity. But if we used, for example, other ranking mechanisms, we could have been able to select assets on a wider variety of criteria rather than just one. So there can be multiple best combinations to fulfill the request. And that's why you need more criteria to select out of this number of best combinations, which one is really the best of it. Since requests are based on bids, most of the time the capacity requested will be available. And that's to say that the virtual power plant will bid in the market they'll say, okay, we think we can provide 500 kilowatts tomorrow. And because it's based on what they requested, most of the time they will be able to fulfill it. Because if I know my virtual power plant is not able to respond to 800 kilowatts, then I will not request for that. I will not bid for 800 kilowatts. I'll bid for what I am confident to fulfill. So the program could be expanded to support other services such as wholesale market participation and bidding. Right now, we used our program to just do some sort of demand response, load curtailment, and DER capacity. But in the future, you can expand a virtual power plant to not just participate in the retail market, but also help DER owners to sell their capacity in the wholesale market if it surpasses what's acceptable in the retail market. So factors to consider, real world scenarios will rely on predicted or estimated capacity in the bidding and dispatching. So as I said, we used historical data here. We used the data from 2020, but in real life, using what you're forecasting, you will be able to fulfill the next day. Service selection should be done indiscriminately, and all assets should be utilized fairly. So you have, as an aggregator or as a virtual power plant, you have a lot of assets in your database, and you need to make sure that you're selecting from those assets fairly and not discriminating against other assets. We think machine learning and artificial intelligence will play an important role, especially in service selection. And to overview the entire project, we started by looking into DERs and demand response, and more so capacity. We looked into generation DERs, we looked into load curtailment and storages, and the ancillary services that this can provide. So we take that and put it through an aggregator, so to increase dispatchability of smaller resources and increase fairness, to better coordinate and planning services. So if you put all the DERs available through an aggregator, it's easy to manage them, and it also increases their chances of being utilized. Technical requirements for virtual power plants, we noticed that communication links and standards are really important. And as we said, IEEE 2030.5 has been selected as the standard protocol for communication in inverter-based resources. Resource commitment through contracts and agreements. As we said, most of the contracts are predetermined, and commitments are made beforehand. So it's not like you're calling a facility and just telling them to curtail their load. They already agreed to do so. Programs with electric utilities, e.g. demand response and net metering. There could be more programs in the future, not just demand response. It could be capacity bidding, could be a wider variety of opportunities for these assets to participate through virtual power plants and aggregation. So we think also software programming for forecasting, asset selection, and fulfilling requests will play a major role. And DNet Soft is already positioning itself in a good place to take on this market. And with that, we welcome any questions.
All right, Jasper and Dylan, thank you. And so I'm going to open the floor for questions from the audience. And for those of you who got the evaluation sheet, please fill it as much as you can, but we'll have some time towards the end. So questions for Jasper and Dylan. Please unmute yourself before you ask a question.
This is Tina Taylor from EPRI. I'm interested in hearing a little bit more about this concept of fairness and non-discriminatory. I did hear how this aggregation helps smaller entities be treated fairly, but I'm curious what other kind of criteria you're thinking of building into the selection algorithms.
So we were thinking about, so once you have like some sort of ranking mechanism, every time one asset is called to respond, you'll have a rank on how frequent that asset has been called. And in the future, you'll be calling on less called upon assets. So you'll have all these assets being utilized almost not because they're the best combination, but also because they haven't been utilized before. Then you select the next assets based on that. So we think about building in some sort of tracking mechanism to see which assets have been used, which one hasn't, and preferring the ones that haven't been used over the ones that have been used before.
Thanks. There's a lot of discussions going on these days, or just starting around the just transition of the energy market and social justice. So, keep those in mind as potential weighting factors or drivers as well as this moves forward.
Excellent point, Tina. That need to be visited many times, and what are the rules and so on. I do know, at least in Pennsylvania, the ruling on community solar, there is a certain amount of, I should say, people cannot buy shares in the community solar, regardless of how they cannot be squatters. You have to have a justification, and so it rewards people who have a need as much as people who are not able to afford it. So it's going to be a long road, but it must be done, as you say, Tina. Good point. Any other questions for Dylan and Jasper? And while you're thinking of the questions, we have John Rogers and Gavin Hatfield, who are the industry project managers and happen to be students here a couple of years ago. So thank you for your leadership.
Yeah, thank you, Rudy. Good job, guys.
Quick question. This is Kenny Seaton from on the other side of the coast in California, Cal State Dominguez Hills. You guys had listed that the most often time is like 8 o'clock in the morning until 4 or something like that. I'm curious where that information came from, because for me, it's always been in the evening, and this last year, it's always been 5 o'clock until between 5 and 9, typically for 90% of the DR events. So I was curious where it's that early in the morning that they're having DR events.
So the data is just basically to have contracts in case there's an event. It's not necessarily that these are actually called upon at that time, but as there's some slight curve, like that curve in the morning, like slight peak in demand in the morning and late in the evening. So I think they are just opening in the summer months when some of the lines could be overloaded, or some there's less supply than there is demand. I think they just open from 8 a.m. to 5 p.m. in general for active load curtailment, just in case it's required. They don't have to be called upon, but I think that's the most duration in which, that's the window in which most of the load curtailment is done.
Okay, thanks. It's just, yeah, it's different. I guess my program is a different one. There's so many.
Any more questions for Jasper and Dylan?
Rudy, this is Jim Robinson. Regarding the assets that were used in the algorithm, what's the concept as far as whether they're under contract to your central algorithm, or are they allowed to participate in the market under other aspects and only participate when you call upon them? Another way of saying this is you could have a lot of assets under your control that are just sitting there standby and not making any money, where they could be participating with somebody else. So it's not clear to me whether you have capacity assets during the actual operating day under your control that are firmly committed to you. Do you have any comments on that?
I believe that's definitely the responsibility of the aggregator to ensure all assets are being used as effectively as they can, and to make sure. I think it's really important to keep everything straight so they're not double dipping and or have that they're biting off more than they could chew. Committing to say a demand response program and also to the wholesale market, a certain amount to the wholesale market. I think that all comes through the aggregator, is coordinating exactly how they're going to be used. If that answers your question.
Yes, thank you very much. I think it's a dilemma that your service is invaluable to the ISO to remove complexity that the ISO would have to go through to get the same service. But it's not clear to me of what the FERC tariff should be to compensate these folks for this, I'll call it ancillary service of being willing to be aggregated. Thank you.
Yeah, I think it's definitely down to contracts signed with DR NetSoft on an individual basis as well.
Any further talk, insights from Gavin and John? It's a very interesting question from Jim.
Yeah, I think Dylan already brought this up, but the concept of double dipping with, FERC Order 2222, ensuring that DERs aren't participating in both the wholesale and the retail programs at the same time absolutely is a challenge. That is almost yet to be fully understood how that part, will be approached, but it is definitely a consideration that we have to look at going forward. Again, going back to that concept of fairness and equity in the energy market.
Okay, we have time for one or two more questions for Jasper and Dylan.
We didn't include it in our presentation because we only just got a subset of their data, but John, can you tell them how much capacity you guys have in just DER assets?
I don't know if I have that off the top of my head. Gavin, do you happen to remember?
I believe Rudy asked the same question a few weeks back. The number was somewhere around 30 megawatts of fuel cell, and just what we're monitoring in terms of PV, we're monitoring about 32 megawatts of PV.
I think that just helps, so that everyone gets the scale of this operation of the virtual power plant.
Yeah, if we look, sorry, it's Alberto Colombo. I think Azure has a plan for 130 megawatt between offsite and on-site renewable energy projects. So that's actually the potential, and we kind of work in a subset of their asset, mostly on-site. So probably, yeah, that's a figure that makes sense. And we just get involved with the PG on a specific program, and we most probably will kind of put in place all what the team has been developed in the real world very soon.
Okay, if you don't have the evaluation sheets or you wish to fill them out, Susan just put it on our chat box. You can download the evaluation form. If there are no more questions, thank you, Jasper and Dylan, and thank you, project sponsors, John and Gavin and Alberto. By the way, for those of you who don't know, Alberto is the CEO of DR NetSoft, and presently, I believe you're still in Italy. Is that true, Alberto?
No, I am finally back in
you're
sunny
back in
California.
Good. Thank
Yeah.
you. All right. Thanks again, Jasper and Dylan. So while you're filling out the evaluation forms, I want to introduce the next speaker. is Thomas Agate. He'll be talking about his project, Nuclear Power in a Clean Energy System. And Thomas, if I'm not mistaken, you're going to play a recording. Is that correct?
Yes.
And but obviously he'll be around for the Q&A at the end of the presentation. So
Sounds good.
do you have access to the screen and everything, Thomas?
Yes, I do.
Okay, good. Go for it.
Good afternoon. My name is Thomas Agate, and this is nuclear produced hydrogen in a clean energy system. And also this project is sponsored by EPRI. So here is a overview of what was accomplished last semester. So last fall, I basically looked at using these small modular nuclear reactors to directly replace fossil fuel generating plants. And so I also examined the economic feasibility of these new plants, either through a carbon tax or a clean energy tax credit. So by only focusing on the electricity sector, I was only focusing on the supply side. So now with this current semester, I am shifting focus to the demand side. So this semester, I am looking at essentially how a hybrid SMR plant could be used to both to generate both electricity and hydrogen, and then this green hydrogen could then be used to decarbonize specific demand side applications within the transportation and the industrial sector. So looking at our decarbonization goals, so if we want to meet that 2 degrees Celsius goal that was set in the Paris Agreement, we need to cut CO2 by about 80 to 95% by 2050. So this essentially means that we need to significantly decarbonize most of the electricity, transportation, and the industrial sectors. So looking at the president's climate pledges, he has pledged to reduce our carbon by about 50 to 52% by 2030. And essentially this would involve nearly $2 trillion in clean energy spending over the next 10 years. And then by 2035, he wants 100% carbon-free electricity. And so this would include the retrofitting of current fossil fuel plants with carbon capture, as well as preserving the existing nuclear fleet, and then of course dramatically expanding our renewable energy capacity. Then by 2050, he wants economy-wide net zero, and he also has included for hydrogen to be used to power certain industrial facilities. And then on top of this, he wants to invest nearly $35 billion into climate R&D technologies. And so these new technologies include utility scale energy storage, carbon capture, hydrogen, and then also advanced nuclear. So here is a video from EPRI, and it basically examines the pace of our future carbon reduction. So in 2003, the Department of Energy established the Nuclear Hydrogen Initiative, and their goal was to demonstrate the commercial scale production of hydrogen using both heat and electricity from a nuclear energy system. And then in 2019, they awarded nearly 15.2 million in funding for advanced nuclear projects, essentially with the goal to improve the long-term competitiveness of the nuclear industry through hydrogen production demonstrations. And also the DOE has this program called the H2 at Scale program, and essentially their goal is to efficiently scale up the production of hydrogen using all clean energy sources, including nuclear. So if you look on the right, we could see that both nuclear and renewables could be used to generate electricity, and then that could be used to produce green hydrogen, and then that could then be used essentially to replace fossil fuels for heating for specific industrial processes like the production of steel, ammonia, the production of synthetic fuels, and also for fuel cell EVs. And then also H2 could also be used essentially as a medium for energy storage. So through the H2 at Scale program, we can look at future demand scenarios for hydrogen. So looking at the current demand, which currently stands at about 10 million tons of H2 per year. And currently most of that is used in oil refineries and also for the production of ammonia. So looking at this 2050 aggressive demand scenario, we could see total demand increase by 6 times to 60 million tons of H2 every year. And this and basically this increase in demand can be attributed to the use of hydrogen in the iron and steel industries for the use of heating, more synthetic fuels, and then obviously to support the increase in fuel cell EVs. And so the current production of H2 currently accounts for about 106 million tons of CO2 every year. And so here we could also look at the potential GHG reduction if we switched all of these, some of these processes from using fossil fuels to using green hydrogen. So you can see that in this 2050 aggressive scenario, by switching all of these processes to using green hydrogen, that would offset nearly 16% of all of our GHG emissions. So currently, most of the hydrogen is formed from a process called steam methane reforming. And then this is known as gray hydrogen. And essentially during this process, natural gas is used both as the chemical feed and also for the source of the high temperature heat. And so currently we get over 95% of the total H2 supply currently comes from fossil fuels. And then shifting our focus to green hydrogen, which is produced from electrolysis. And then obviously this process would use electricity from renewable or nuclear sources. Obviously this would have zero carbon emissions, but unfortunately electrolysis only accounts for about 3% of the global H2 supply. So here is a development timeline of the SMR. So in 2013, a nuclear energy company called NuScale, they actually won a $226 million award in DOE funding in order to develop SMR technology. Then by 2016, they actually submitted their first 50 megawatt SMR design for evaluation by the NRC. Then in 2020, the NRC finally approved their design. And then they have plans to apply for their final 60 megawatt design by 2022. And then they plan to have their first 12 module SMR plant to be fully operational at the Idaho National Labs by 2027. So here's a overview of the small modular reactor. So in this scenario, each of these modules would have the capacity to generate either electricity or green hydrogen. So a single of these SMR plants could have up to 12 of these SMR modules. So basically creating a 720 megawatt total plant. And then each of these SMRs would have the capacity to use high temperature steam electrolysis in order to produce this green hydrogen. And because of their standardized design and also due to their small size, SMRs could be constructed at a factory and then basically shipped to the site. And so one of the advantages is that they could be installed directly at the site of the energy or the hydrogen consumption. And also because of this, because of their factory fabrication, they have lower production costs, faster construction times, and they are very easy to install. And also due to their modularity, they have the ability to load follow solar and wind. And this can be accomplished essentially by changing the number of modules that are either producing electricity or hydrogen. So if the supply of solar and wind is at a peak, then essentially the SMR plant can then shift towards producing more hydrogen. And essentially at this point, it wouldn't be profitable for the nuclear plant to generate electricity. However, when the supply of solar and wind is at a low point, then the SMR plant could shift towards producing more electricity at a time where it would be more profitable. So, so as I mentioned, SMRs basically create H2 through a process called high temperature steam electrolysis. And so this is basically accomplished by using steam and also electricity from the nuclear plant to basically split the H2O into H2 and O2. And so this process is more efficient than conventional forms of electrolysis. And so just one of these SMR modules has the capacity to generate nearly 18,000 tons of H2 every year. And obviously this would offset about 168,000 tons of CO2 every year. And so if we want to replace a mid-sized steam methane reforming plant, a 6-module SMR plant would have the hydrogen production capacity in order to replace one of these plants. So now we are going to shift focus and basically examine how this green hydrogen could be used in the industrial sector. So the EIA projects that by 2040, over half of the energy consumed will be by the industrial sector. And specifically, industry will be especially hard to decarbonize due to the use of fossil fuels as both the chemical feedstock as well as the source for this, for high temperature heat. And so green hydrogen is often seen as a possible option to decarbonize several of these industrial processes. So a 6-module SMR plant could theoretically supply enough green hydrogen for a commercial ammonia plant or a mid-size oil refinery. And so other hydrogen applications in industry, it could be used as a chemical feedstock for several of these industrial processes, such as ammonia, steel, as well as synthetic fuels. And then also it can be used as a source of industrial heat for furnaces and kilns. So shifting focus to the transportation sector. So even though battery-powered EVs are more energy efficient than fuel cell EVs, it is actually projected that by 2050, fuel cell EVs could actually make up to 20% of the total vehicle fleet. And this would include nearly 400 million cars. So a single SMR module could provide enough fuel for about 38,000 of these fuel cell EVs. And then for aviation, green hydrogen could be used to basically make synthetic fuels for planes. So looking at the current demand for H2, it would currently take about 46 of these 12 module SMR plants in order to completely supply our total demand for H2. And so this would obviously offset CO2 by about 106 million tons of CO2 per year. And then shifting focus to the 2050 aggressive demands scenario, nearly 280 of these SMR plants would be required. And obviously, as I said, under this scenario, nearly 16% of all of our GHGs would be offset by the use of green hydrogen. So now looking at the cost competitiveness of nuclear high temperature steam electrolysis, we can compare that to the conventional steam methane reforming. So the current federal target for the green hydrogen levelized cost is about $2 per kilogram of H2, and so we can see that this target is actually met when the SMR plant is capable of producing electricity for a cost of less than $44 per megawatt hour. And so then looking at the current levelized cost for conventional methane reforming, which is about $1.59 per kilogram, we could see that nuclear electrolysis meets this when it's able to generate electricity for under $30 per megawatt hour. And obviously, if a carbon tax was also implemented, this would make nuclear electrolysis more financially viable against conventional methane reforming. So just to summarize, green hydrogen can be used to decarbonize parts of the of both the transportation and the industrial sectors, and it has the potential to offset total emissions by about 16%. And then obviously this will help us reach net zero by 2050. And so specifically these hybrid SMR plants, they have the capacity to produce green hydrogen at the site of consumption, while also supplying clean and reliable electricity to the grid. And then obviously due to their modularity, they have the ability to load follow as well as supplement solar and wind, and by also generating green hydrogen. This would also increase the financial competitiveness of nuclear plants. So with that, I would like to say thank you. And are there any questions?
Thank you, Thomas. Questions for Thomas? You can unmute yourself before you ask a question.
Good evening, Thomas. This is, oh, wait a minute. Let's make sure you can see me. Horace Davis here with Con Edison. Very interesting presentation and concept. My question for you is, you had mentioned about these modular units providing hydrogen and then being able to, based on market rates of electricity, being able to shift between generating electricity and generating hydrogen. What would the time span to transfer between producing hydrogen and electricity be?
Yeah, so basically, I'm pretty sure it could take up to a few, I think it's only like a few hours, or I think it's as short as I think it's like as short as like I think like 30 minutes or up to like 2 hours.
Okay, thank you. Thank you so much.
Thank you.
Well, there's no doubt nuclear will have a large role in this meeting 2030, 2050 goals. And we have very good operating experience in the US, and I think it's a very powerful technology capability that we have to go forward with. Recently just heard about Dominion Energy getting a life extension on their Surrey plant, and it's always good news.
Yeah, absolutely. And one of the reasons why I asked the question is obviously with green energy and renewable energy, you're dependent on the sun, you're dependent on the wind, and to have the ability to transition, increasing production in electricity when it's needed, and then allowing the green energy to be utilized when available. Otherwise, battery storage is going to be the key. Not going to be able to do much unless we're able to shift the resource to a time when it's needed.
Yeah,
yeah,
absolutely. Good point, Horace. Any other questions for Thomas? Yes, Al?
Thomas, in my opinion, the problem with nuclear right now in the United States is, what do you do with all the spent fuel? The United States has obviously collected billions of dollars over the years for the Yucca Mountain facility, and they've never accepted one shipment of nuclear fuel, to my knowledge. All the utilities that are using nuclear generation have enormous spent fuel pools and on-site storage. It seems like this is just another problem waiting to happen. It seems like if we don't solve that storage problem and open a central storage facility, that nuclear is just going to continue getting in its own way. Have any thoughts on that?
I do know that there is a new type it's called a traveling wave reactor, and I believe that is from a company called TerraPower. And so basically, and so basically that that can actually basically like a used spent fuel. I don't know when that will be available, but yeah, I mean, it's an idea.
Okay, I had not heard of that, so that would be interesting to see.
Tina, did you raise your hand, Tina? Or, oh, I'm sorry.
No, just acknowledging that the waste questions always come up with nuclear, and the current paradigm of storing used fuel on site, while not ideal, is safe. So it's not really an issue about that. But whether we build more nuclear or any generation asset for electricity, we do need to think about the whole life cycle of waste, and also the front end, the resources that we're using. So it's a good question.
Yep. And Thomas, your answer too was very pertinent. I think that's Bill Gates' TerraPower, that's his company, I believe, or at least he's funding it. Yeah. And I heard, Tina, you may know more about this. I think they got funds from DOE for a demonstration of that capability, and for quite a sizable amount. So hopefully that demonstration, if it works out successful, it's a very feasible plan for spent fuel consumption.
Yeah.
Okay, one last question for Thomas, anybody? Okay, if there are no more questions, thank you, Thomas. And again, reminder, in the evaluation sheet, please fill this out for both the projects that you heard. And so in our agenda, we have about 10 minutes for you to be able to fill that out while we prepare for the next event. If you haven't filled out those evaluation forms, please do so. It can be handled electronically. So I'll give you a few minutes to get that done, and then we'll get on to the next item in the agenda.
Rudy, it's only set up electronically, just so you know. We didn't do the paper form this year, the downloadable form. It's everything is through Google Form.
High tech.
Yeah.
So while you're filling it out, I will get my presentation ready to introduce Clint. All right, so let's move on to the next item. I'm very pleased to have in our presence Clint Carter, who's a longtime friend and colleague of mine, and has had a very illustrious career and still continues to be doing some wonderful things. I met Clint more than a couple of decades ago while we were involved in a project while I was at EPRI looking at equipment condition monitoring to automate this and basically have this as a tool, for utilities to be looking at mounting operations and maintenance costs and to be able to reduce this. It was a very novel and a very disruptive. It was a very disruptive idea, if I can remember, because utilities just can't go willy-nilly into this. While he was at what was then called Texas Utilities and now it's called Luminant, I remember going through all these business cases that Clint and his team prepared. And more often than not, it was kind of senior leadership that would step in and say, yes, we want to go forward with that process. Anyway, that was many years ago. And today he's kind of, that has blossomed to one of the premier centers in the world, the Power Optimization Center, which has a capability of looking at just what Clint had envisioned back then. This capability has been emulated by several other U.S. utilities as well as in Europe and elsewhere. Clint has now, he's been deputed to, I believe, a company called United Service Alliance, which works with the DOE. And he's the director for fleet modernization for the nuclear fleet. And as you heard from Tina and as you heard from Thomas, nuclear is our ticket, as we go towards decarbonization. And Clint is right in the middle of some very interesting projects that looks to improve this capability. So Clint, he has a career of over 35 years. He's worked in engineering, operations, and management. He's a senior nuclear reactor operator, holds a PE license, and he's just a great guy to be around with, Clint. So without further ado, Clint, you have the floor.
Well, good afternoon, everyone. I appreciate the opportunity to participate in today's event and certainly appreciated the previous two presentations as well. Very, very exciting stuff going on and much appreciated being a part of that. So what I'll do is I'll share my screen and then walk through an overview presentation associated with nuclear. So,
wow,
can everyone see a blue screen now? Hopefully.
Blue screen, right? Mm-hmm.
All right, very good. Okay. So what I'd like to talk about today is a need, an opportunity, and an initiative to facilitate transformation of the legacy nuclear power industry. I'll talk about the need for this transformation, what it's all about, with centralizing around a theme. We've talked a bit today about high operating costs of the nuclear industry, plants being shut down and that sort of thing, and the benefits of preserving nuclear power, preserving atoms for peace in today's economic reality. So with that, I know many of you appreciate the Atoms for Peace perspective. Some of you, this may be a new concept, but Atoms for Peace was a speech that was delivered by President Eisenhower back to the UN General Assembly in 1953. This was in the midst of the Cold War with the Soviet Union not so many years following the conclusion of World War II and the dropping of the atomic bombs. And so in those days, the world feared nuclear holocaust, and the Cold War tensions were high. And President Eisenhower promoted this idea of taking nuclear technology and converting what had been created to something that could actually be constructive and ultimately benefit all mankind. So developing, as one of the things that he promoted, was using nuclear atomic power to generate cheap, abundant electricity to essentially power the globe and provide cheap electricity to folks that may not have electricity. And so that was the Atoms for Peace speech that President Eisenhower presented. So let's fast forward to today. And what is our situation today? Well, nuclear power has become a crucial component. Here in the United States, it's crucial for maintaining our national security interests. That includes energy security, as well as our place as a global leader with around nuclear technology. Also, nuclear power has become crucial for maintaining stable electric grid conditions. In fact, it is the only large-scale electric energy source that is carbon-free, that can maintain grid stability as we migrate to renewables such as solar and wind and battery storage and those sort of things. Nuclear is critical for maintaining grid stability, as some of those other legacy carbon-based generating capabilities diminish over time in favor of renewables. And lastly, achieving our environmental goals. We've talked today a number of times about zero carbon emissions from nuclear. And without nuclear, the Clean Climate Initiative, we haven't got a chance of meeting those 2050 goals utilizing existing technologies that are available today without nuclear. So nuclear has become crucial. But just last Friday, here's a shot of the Indian Point Energy Center. I suspect many of you are aware of what happened last Friday. A couple of very important milestones. First, Indian Point Nuclear Unit 3 achieved the longest continuing sustained run in the history of any nuclear operating unit. I'm sorry, I don't remember the exact number. It's over 700 days of continuous operation. Also on April 30th, they shut down the last operating unit at Indian Point for the last time, never to operate again. And so what's going on here? Why did Indian Point shut down? And well, there's challenges that the legacy nuclear industry is facing today. We've touched on things that are happening. And what I'd like to do is to invest a few slides to explore what's going on and perhaps some things that we can do to turn the tide, if you will. So the bottom line is economics. The industry's economic competitiveness is diminishing. There's disruptive technologies that have been brought to bear. This includes fracking technologies, energy efficiency improvements, increasing production costs, and lowering market prices. Once again, we've improvements in efficiencies, energy conservation. The market has changed substantially. However, nuclear's operating costs, while we have been successful reducing them to some degree, are still less secure than less competitive than they really need to be for sustainability. following the Atoms for Peace initiative, as we began to commercialize and design commercial nuclear units and begin to build them, the promise of nuclear was it was going to be too cheap to meter. And we were not too far from that concept. For many, many years, nuclear was the cheapest generating, large-scale generating technology there was. And over the years, as activities happened, 3 Mile Island, Chernobyl, 9/11, for example, we've added layers and layers of regulation on top of the nuclear power industry, both formal and informal. And so costs went up, but due to market conditions, the industry could absorb those costs and still be able to return an attractive margin to investors. But with the advent of fracking technologies and the plummet in the energy market, nuclear could not respond to that because of all of the burden that we have assumed. And so what happened at Indian Point last week is just the most recent in a series of nuclear power plants that have closed principally because they're no longer economically competitive. And if you look at the industry in the aggregate, almost a fourth of our operating nuclear plants are at risk of shutting down in the not so distant future, unless something radically changes. And so those changes, if we are to sustain the nuclear power industry, it mandates that we find ways to reduce our operating expenses. I'll be talking about an initiative we're working along with through the Department of Energy to demonstrate how we might transform our core business processes through technological innovation to drive costs out and to help sustain their economic competitiveness. And so I've talked a bit about what's going on, but what's the bigger picture that's happening? It's not just the nuclear industry, but it's the entire energy industry, electric power industry. So what's going on in the external environment? And understanding that also helps us understanding possible solutions. And so actually what's going on, we're in the midst of a revolution, a disruptive revolution. Not like the ones that George Washington fought, but we are in a technological revolution. Klaus Schwab, he's the chairman of the World Economic Forum, and a cornerstone or a theme that the World Economic Forum has been promoting for the last several years and holding many sessions on as part of their annual event in Davos and elsewhere around the world. Klaus comments that we stand on the brink of a technological revolution that will alter the way we live, work, relate to one another. He says this is going to scope and complexity. This is going to be unlike anything humankind has experienced before. And he calls this the fourth industrial revolution. So this is disruptive technologies at its a pinnacle of disruptive technologies, and we're being challenged by this today. There's benefits, but also there are also detriments unless we can accommodate what is happening. And so I've talked about this concept a number of times over the years in audiences filled with seasoned utility professionals, and in a group of 100. If I ask how many of you have heard of the fourth industrial revolution, I might get 4 or 5 hands. So I hope that many of you today, this is a familiar term. If not, I'd encourage you to take a look at the World Economic Forum's website and learn more about it. It is fascinating. So I will share a bit of background. If we are in the fourth industrial revolution, there must have been 3 that came before it. So just a little background here. So it all began in the 1800s with the first revolution, where we harness the power of steam and water and mechanized material developments. We evolved in the second industrial revolution to applying electric power and specialized different parts of our labor to improve our ability to mass produce. In the third revolution, we added computing technology and automation. So digitization of processes to further improve production capabilities. And lastly, the fourth industrial revolution. This represents a convergence of cyber intelligence with physical systems, actually blurring the line between the two. But the things that we're seeing today as part of the fourth industrial revolution, things like 3D printing technologies, driverless cars, and many of the other fantastic capabilities that are that we're all coming to accept is becoming the new reality. And all this evolution is the pace that it's impacting us is become exponential. It's technology is moving faster than industry and much of society can keep up with. And so some people may recognize, I don't recall when this actually happened, but in the late 1950s, Sputnik, the Russians, the Soviet Union, launched the first artificial satellite into orbit around Earth. And for the first time, American families could stand out in their backyard and see that satellite flying over their homes, and fear gripped our nation. How long would it be before an artificial satellite might be able to do harm, flying over us could do harm? So we had our Sputnik moment, and we all know that concluded with President Kennedy's initiatives to place a man on the moon by the end of the decade, which was accomplished. And so really the nuclear power industry, the electric generation industry, we are going through a Sputnik moment, just as we did back then. Everything's being disrupted. And Uber. Today, Uber is commonplace, but think about the disruption to the taxi industry that resulted in Uber. Other technological disruptions, Kodak, largest film camera company back in the analog days, digital photography, totally obliterated that company. These iPhones that we all carry around and take for granted the capabilities. Just a few years ago, it would cost almost $1 million to buy all the equipment, hardware, and capabilities that we all carry around in our pockets and purses these days. Think of all the industries that have been disrupted. And so now the same thing is happening to the electric power industry, and particularly nuclear. How do we transform an industry that is so burdened, laden with regulatory overhead and complexity? It's going to require new ways of thinking, and industry transformation has become a matter of survival, honestly, for our legacy nuclear industry. So transformation. Okay, I'd like to talk for a moment about evolution. Where have we come from? Where are we going? Some of you may see an individual that looks a lot like the Geico caveman down in the corner. That's actually a nuclear plant operator back in the early days of our industry. I can say that because I was one of those cavemen. So where have we come from and where are we going? And so I know there's a lot of words here, a lot of thoughts. Think of it this way. Think of this as an XY axis. The y-axis being the technology that we apply to generate, transmit, and share electrical power. And the horizontal axis represents how we as a culture, society apply technology to achieving those goals. So back in the caveman days, we operated our plants very manually. We collected information in a very manual fashion. We walk around with paper clipboards and pencils, taking readings off of analog gauges. We would operate the plants and we would only perform maintenance when something broke. So over time, we've developed more semi-automated operations. We've evolved to develop preventive maintenance activities so that our plants can operate more reliably. We adopted predictive technologies, and we've migrated from time-based preventive maintenance to condition-based maintenance. And so really what we're seeing over this timeline from our early days is we now have developed the capabilities and the technology to optimize our workforce. And this is critical for nuclear. The single largest cost of any nuclear power plant are the people that are required to be there to operate and maintain the facility. And that number from the early days of the industry, an average 600 megawatt plant, it's probably got twice the workforce that it had when that plant opened up because of all of the overhead. Technology offers an opportunity for us to automate a lot of the things that we are still doing manually: data collection, automate analytics, automate regulatory compliance where possible, and that sort of thing. So workforce optimization. And going forward, this will lead to a convergence of all of this. Cyber capabilities converging with physical science to enable a digital workforce of the future. One joke is in the nuclear plant of the future, there'll only be 2 operators in the control room: a man or a person and a dog. The man's job is to feed the dog, and the dog's job is to bite the man if he touches anything. So this is ultimately where we could be heading. And evolution, as you know, is a survival of the fittest. This will happen, whether we transform or not. This is what's happening. And so rather than evolution, we as an industry should think of transformation. And the nuclear industry's imperative is to accelerate this transformation. So transformation's a journey. How do we know when we get there? And so I'm going to talk here in a moment about this DOE-sponsored initiative that we're participating in that's designed around industry transformation. And as we got into this project, some foundational principles, we built some our project around some foundational principles. Not all these are completely accepted by the industry, but this was where we started. Nuclear power has the capability to remain cost competitive without subsidies or other artificial considerations in the long term, getting back to the days of virtually too cheap to meter. Looking to core business processes to be standardized and then optimized and shared more completely across the industry. Automating repeatable tasks, the operators with clipboards in the plants, using technology to capture that data, analyze it, and virtually eliminating human inspections in favor of advanced technologies and remote centralized monitoring, and taking traditional fixed expenses that each nuclear plant assumes individually and variabilizing those and sharing the costs incrementally across a larger population base. And this represents actually a bold new paradigm or challenge that our industry needs to face. And so I'd like to talk about an initiative that is founded around those principles. We call it the Advanced Remote Monitoring and Diagnostic Services Project. This is a project in partnership with the Department of Energy and the Utilities Service Alliance. And I'll talk a little bit more about all the partners in a moment. Some of you may be unfamiliar with the USA Alliance. USA Alliance is a not-for-profit cooperative that is that has a membership base representing a number of the smaller, maybe single or one or two site nuclear utilities across our nation. And the USA's role is to enable these smaller nuclear utilities to have economies of scale, like the larger fleet level operations, so they can work together to get more effective service contracts, labor contracts, be able to purchase things in bulk and share, as opposed to the higher costs of going individually. And so the USA Alliance, we have 6 different member utilities representing a dozen nuclear reactors across the nation. And so this particular project, the vision of this project, is to assist in preserving the competitiveness of our nation's nuclear energy supply by transforming core business processes through the application of advanced technologies. We're working with Idaho National Labs, and you may recognize the logo on the far right there. Lehigh is also participating in this initiative, and I'll talk a little bit more about that as well. You can see the USA member utilities and the nuclear facilities that are also participating in this industry technology demonstration. Just for a check, can you all still hear me? My machine is just locked up.
Hear you.
Okay.
Loud and clear.
All right. Well, I'm not certain what's happening here. I'm going to stop sharing for a moment and see if I can escape and get, for whatever reason, I was locked up. So there we go. Am I still screen sharing?
You should be able to.
Okay, hang tight. Okay, I'm going to be sharing again. And here we go. Okay. So the scope of the Advanced Remote Monitoring Initiative is threefold. First, Rudy mentioned Luminant's Monitoring and Diagnostics Services Center that's located in our corporate headquarters in Irving. We call it the Power Optimization Center. You can see on the upper right. The POC is a 24/7 real-time ops support center that looks at real-time power plant performance efficiencies and reliability of systems and equipment, and use machine learning technologies to try to get ahead of problems. As a part of this project, we will have 5 participating nuclear units that will be monitored by the POC to demonstrate to our industry the value contributions such as centralized service can deliver. Second, the development of NewSuite. This is a shared services platform for all USA participating members that we ultimately, our intent is to share this with the broader industry. So NewSuite is comprised of modules, much like the apps on the cell phone the iPhones we all carry around. So developing standardized technology apps that will help the power plants perform different workflow processes through technology to drive costs down. Armed with cyber-assisted analytics, machine learning, AI technologies, and enabling us to expand and monitor more of the power plant through online capabilities. I talked about transformation several times, so business process transformation, expanding nuclear plant monitoring, automating compliance, and centralizing our monitoring analytics, and then dispatching valuable human resources by exception when the automated systems identify some emerging anomaly in the power plant. And then you can see on the right, as a part of this project, we'll be deploying additional sensing technologies, radiation, cameras, acoustics, temperature, humidity, smoke detectors, and bring all of that together into the NewSuite environment to enable us to monitor real time what's going on in the plant without the need for humans to be constantly roaming the facility looking just to verify that everything is the way it should be. Those valuable resources can be focused on more productive activities while technology monitors the plant and enables us to drive cost out of the business. So new suite, the modules are developing as part of the ARM project. You see here on the right. So expanding online component monitoring and applying some machine learning technologies. We'll be building out online capabilities for transformer health using some machine learning technologies developed at Idaho National Labs. Online thermal performance and optimization, understanding moment by moment where we are from a thermal efficiency perspective. And being able to recognize real-time emerging losses through cycle isolation points. Automated regulatory compliance, deploying wireless sensing technologies in the plants in order to accomplish shiftly regulatory surveillance requirements without the need for human manual effort at all. Reducing operator rounds. Again, deploying field sensing technologies in the plants to demonstrate that we can virtually eliminate operator rounds and inspections in favor of technological monitoring. Monitoring remotely radiation work activities going on in the plant to reduce radiation exposure and also the cost of human resources to provide radiation protection oversight. Process anomalies detection, developing an intelligent machine learning algorithm that can monitor the plant digital control system, the plant computers, to identify emerging anomalies and be able to understand, is this an instrumentation issue or is it a real process change? And by the way, this process anomalies detection, this is where Lehigh Engineering is participating and helping us develop in partnership with Idaho Labs, this process anomalies detection machine learning capability. Lastly, Firewatch program, automating roving and dedicated inspections in the plant to monitor for emerging fires, being able to develop portable systems that can monitor and remotely notify if smoke or fire is detected, rather than a person having to be constantly roaming, trying to identify things. So these are just examples of the first modules or apps that will be part of NewSuite. And it's our intention to add to and expand these capabilities going forward. So that's the Advanced Remote Monitoring Project. And taking this to beyond this 3-year industry demonstration initiative, we see opportunities for technological transformation. It will play not only an important role for preserving legacy nuclear operations, but next generation and small modular reactor, building this type of capability, an opportunity to leapfrog the workflow and the processes in next generation reactors based upon our learnings, and similarly provide those new learnings coming from small modular deployments, next gen, bringing those learnings back to the legacy fleet. So we see a sweet spot for technology to help us sustain high levels of performance, low operating costs of the legacy fleet, while accelerating the maturation of next generation reactor technologies through advanced online monitoring. Benefits for the participating utilities. We see opportunities here for strengthening safety, performance, and reliability. We are looking at objective third-party evaluation, this industry demonstration, to determine the actual benefits and the opportunity to develop a standardized platform that the participating utilities will own. So they are not subservient to third-party software providers and annual license fees and that sort of thing. The nuclear industry, we are generating a strategic roadmap for transformation based upon our learnings from this project, and a supporting business case for business process redesign through the application of technology. Our nation, and why the DOE is invested in this, is to help us sustain the large-scale benefits of nuclear power, while preserving our nation's single largest source of zero carbon generating capacity. and ultimately to reduce the need for new and ongoing subsidies to help sustain nuclear. And so in closing, technological disruption, environmental priorities, economic realities are bringing about a radical transformation of our industry. It is our intention to work together to preserve nuclear power for the benefits of all mankind and to continue to sustain Eisenhower's vision that he promoted as a part of Atoms for Peace. And so with that, I thank you for your attention.
Thank you, Clint. Can you all hear me?
Yes.
Good. Questions for Clint? You put a lot of things on the table.
Clint, this is Jim Robinson, former friend of many nuclear plants since I helped build the transmission for them. One of the observances that I see is we're having difficulty keeping nuclear competitive because our legacy design intentionally included them as base load and not intending to follow load or frequently reduce output. Many of the existing plants produce a fair amount of xenon gas if you reduce them, and they're not able to go downward in output and quickly come up. Are the new modular units and maybe the Utilities Service Alliance going to be able to be designed to be more responsive to cost signals that plummet when solar is on and reduce output as necessary if the price on the market goes below the nuclear price? Is that on the horizon, or is that a technological super problem we're not likely to fix?
Well, thanks, Jim, for that question. I guess I'll answer it in two ways. First for legacy, and then second with modular. Legacy nuclear plants, you're correct, they were designed, well, they've been operated principally baseload for most of their careers. And if you go back and look at history, coal was the same. Coal was designed for baseload operation. And before that, the legacy natural gas, baseload operation. When the reality of economics hit those industries as well, those technologies, the same reaction was, we can't operate these plants. We can't load follow. These are baseload units. Well, gas and coal all successfully converted. And if you look at many of our plants, my plant, Comanche Peak, while it's been a baseload unit since it started up, it was designed for load follow. We were designed to go to 50% power overnight and back to full power before peak load in the morning. Many other plants were too. We abandoned those. And yes, load follow operations in a nuclear plant generates poisons that have to be managed to maintain axial flux profiles within limits. And there is potential for fuel clad damage. But we've addressed those, as some plants are now beginning to load follow, and the fuel manufacturers have developed more tolerant fuel that could support. So there are opportunities, I think, for nuclear power to reconsider and to make the necessary physical adjustments in the plants so that they can accommodate some degree of load follow. Also, things like hydrogen production and powering behind the meter generating needs, for example. Those are opportunities also for both legacy nuclear and next gen small modular reactor technologies. So when the price of power goes down and the nuclear plant isn't competitive, then that's a good time to generate hydrogen perhaps and store that, and then put that back on the grid when the economics are there. So hopefully that answered some of your questions.
Yes, it does. I think nuclear is the future, and part of that future, I believe, needs to be load follow for a variety of reasons.
It just has to be. And, the idea, once again, if, at low demand, like in Texas at night, when the bulk of our power is being provided by wind from West Texas, the market clearing price of power is actually negative. So we're losing money to keep our plants running all night so we can be there for tomorrow. But what if we could shift and just start producing hydrogen when market prices fall beyond our profit point, and store that and then be available. So continue to run that unit at base load if possible, but store that energy in hydrogen or batteries or compressed air or whatever technology would make sense for the situation.
Thank you.
Questions for Clint?
Hi, Clint. This is Larry Amy. Thank you for a wonderfully constructed presentation. I love the circularity of how you started and how you ended. My question is this, you're proposing a technical solution that reduces operational costs, but isn't it also a political and educational problem? In other words, we have an image of it being risky, and therefore we've got some public repercussions. So isn't it a combination of reducing the operating cost and also going on a lobbying effort or a marketing effort?
Absolutely. Larry, I completely agree. You know, despite the fact that nuclear has the predominant safety record of any industry on the planet Earth, impeccable safety record, people still associate nuclear with bombs and deadly radiation. And you know, the reality is, yes, we've had a couple of disastrous events, Fukushima and Chernobyl and 3 Mile Island. Well, 3 Mile Island, no one died. Everything went wrong in a US nuclear power plant that could possibly go wrong, and very little happened. You know, beyond design basis accidents, you know, 50-mile wide meteorites hitting a nuclear plant, you can't stop that. Tsunamis, okay, stuff happens. But those are 2 isolated events, and you go compare the effects of those events relative to other large industrial events. The consequences were small in comparison. Politically, yes, how many times have you seen a promotion for safe nuclear power on a commercial during the Super Bowl? Or, you know, we don't promote it. We do a terrible job as an industry promoting the value of nuclear technology. And I think that needs to change. Somehow we need to get the word out. And there are many forums and initiatives now. In fact, many environmental organizations are now promoting nuclear power in recognition of the zero carbon contribution. So, Larry, it's highly needed. I think that's, you know, as big of a challenge as the economics are, the solution is a technical thing. Engineers can solve that problem, but we need society and our political leaders to help us promote this to the people to gain societal support.
A follow-up, if Rudy will permit. The fuel mix in the US versus the fuel mix in France. So industrialized fuel mix, I would suggest that France is, I don't know the numbers, but France is high and we're relatively low. They've managed it well. And then my second question I'm really loading on here is, has Secretary Granholm tipped her hat in terms of policy preference for nuclear?
I can't speak a lot to you're talking about the energy mix in France. Are you talking about the nuclear being predominant over other technologies? Is that what you're driving at?
Yes.
Yeah,
in other words,
yeah,
is there
so,
a model out there that countries that have done it perhaps better than we have?
Different. All, you know, it's got all owned by the government. So the government built, you know, what are they, probably around 70-80% nuclear. Well, the government built those facilities, where ours was in a private sector, and we had subsidies and things to promote it, but that was a much different thing. What I am seeing is coming from the Department of Energy. I'm not current with a lot of the new secretaries' initiatives, but what I am seeing for the first time is a lot more legislation coming out of being circulated through Congress and coming out that is promoting the sustaining the legacy nuclear power industry for all of the new environmental goals that that President Biden has put out as part of his policy / agenda. So I think we're going to see more support. And in fact, I was in a Senate office meeting with some of the folks there maybe 2 years ago. They acknowledged immediately, all of our legislation is, and the funding that we're creating and making available to the Department of Energy is all next generation small modular reactor. We're doing zero for legacy nuclear. Now you're seeing legislation coming out of Congress that is also targeting sustaining legacy nuclear as well. So I'm very encouraged by what I'm seeing going on within the Beltway.
Thank you so much.
Very good. Any questions? Al?
Yeah, Clint.
Yeah, Al.
Just the question that you were asked there about the proliferation of nuclear in France. I can't speak for today, but I know that 10 years ago, they were a little over 80% nuclear. And as you noted, the key to that is it was owned by the government. And they had the spent fuel storage facility and everything. And I believe at that point in time, the US was around 20%.
Yeah.
If I think we all know that it's probably declined since the 20%.
Yeah, we were just above 20. I think we're right below 20% now. I think we have 94 operating units left. And you know, I think Al, it might have been you that asked the question on the spent fuel issue earlier. I can't recall now exactly who it was, but the high level radioactive waste, don't hold me exactly to these numbers, but you know, while all of our high level spent fuel is still at the plants that it was consumed at here in the United States, we brought it all together and we put it in the New England Patriots on their football field, 100 yards long. We brought it all together. It'd be 100 yards long, size of the football field, I think about 30 feet high. That's the extent of the high level waste our nation has since the beginning of the commercial nuclear industry. It ain't a big deal. If we, you know, it's being back to, I think, Larry's questions around the politics. The politics is what keeps Yucca Mountain from opening, not science and the technology and the fuel itself. It's politics.
I couldn't agree more. My understanding is they could start taking it next week if it was allowed to be picked there and safely storing it.
Excellent. More questions?
Yeah, Rudy, Jim Gallagher.
Hey, Jim.
Hi. Yeah, a question. I've been involved personally for a long time in energy, you know, going back to even when I was young, going on tours with a student group at 3 Mile Island and working at TVA and elsewhere. And then 20 some years here at the Public Service Commission in New York. There are lots of discussions going on right now about where we're going, how we're going to meet, you know, Biden's goals, but in particular, most of the discussions are about how are we going to meet New York's very aggressive goals. I don't hear anyone, at least in the New York discussions, and New York's 10% of the country, talking about modular nuclear. Who is the proponent? I mean, who should be in the state making those arguments? I'm not hearing it from the utilities, but I don't see an effort underway to really put modular nuclear on the table. And I'm just wondering that I feel like there's a disconnect somewhere of all the discussions and the planning and the thinking that's going on right now and the presentation you just gave.
Yeah, yeah, Jim, I see the same thing. And you can't expect it to come from the utilities,
Right.
really, at the end of the day. I mean, it's an economic thing. The utilities will build small modular reactors when they can make a buck doing it. That's their whole objective, is to generate reliable power and at a profit, period. Just as legacy commercial technologies, just as coal, just as renewables, all of this has been promoted by national policies, legislation, subsidies, initiatives to move our nation in that direction. Small modular reactor technologies will get traction when it becomes economically, when the industry can be economically incented to move in that direction. The technology's got to be viable, it's got to be proven, and then it's got to be sponsored by our government and our political leaders. It'll happen then, is when it'll happen. Just look at history. It may not happen fast enough, which is why, again, we need to preserve legacy as long as we can. We've got many, many years before we could replace legacy and replace fossil, as we shut down fossil in favor of renewables or small modular reactor technology. That's going to take literally decades to make this transformation.
All right, thank you.
More questions for Glenn? Going once? Well, thanks a lot, Glenn. Again, a very informative talk. As usual, you put a lot of things there on the table, and I hope, we have the young generation motivated to get into the industry. And one final comment, some of the large reactors are being built in China. And, some of the standards that were all kind of developed here may well originate for the next generation nuclear from China. And I also recently read EDF has bid, and I think the Indian government is going to go ahead with 6 1,500 megawatt reactors. So some of these, the newer large reactor technologies are in the East, in China and India. It's not that we cannot it's not that we cannot catch up, but I think we have the expertise here. Yeah. I mean, we have 50 years, 60 years of operating nuclear plants very safely. So
that's right, we do. And that's where the whole national security, the benefit of domestic nuclear. Right now, we still are the global leader in nuclear innovation and technology, but we are at severe risk of losing that to Russia, to China, to Korea. And what will the world look like if that transition occurs? It most definitely becomes, with, let's say, Russia expanding their technology across the globe, if they're powering those other nations, then they have the political leverage, the footprint, expanding footprint of Russian presence, for example. And so that is ultimately a security threat to us, which is one of the primary fundamental drivers behind preserving our place as the global leader in nuclear technology for the world, and for the benefits of maintaining peace and prosperity around the globe.
And Lehigh very much looks forward to working with the United Service Alliance and Idaho National Lab on this project, Glenn, and thank you again.
Thank you all.
All right, so we're going to move on to the next item on the agenda, which is the Industry Advisory Council meeting. And what we have on the agenda is, first of all, want to hear from the members' feedback on the project symposium, the topics that were addressed, and students' performance. I know you've documented this in your evaluations, but just want to hear some from some of the members here. Any thoughts on this spring session?
Hey, Rudy, I'll have a say. I raised my hand digitally. I didn't know how we wanted to do this, but I thought the topics were definitely some of the more progressive topics, kind of on the forefront of the industry. I thought that was fantastic. Talking about upcoming trends in nuclear and demand response, and just this kind of underlying idea, right, of disruption and energy equity. I think those are going to be huge topics going forward here. And I thought that the information presented by the students, I think everybody did really well, and was happy with the information they delivered.
Good, thanks. Any other thoughts, feedback, questions?
Yeah, my comment was going to be the same, Rudy. I thought the material was very grounded in where the technology and state of the art is going. I also think it after being in a couple poster sessions over the last 2 years, it's been a very smart progression in getting more market focused, which I thought was very good. I thought all the presenters did quite a good job.
Yes, and of course,
Rudy, I'm going to agree with both. I like the DER focus.
Thank you, David. And what I was going to say is it's because of projects that originate from your side, industry side, it keeps us kind of occupied and be, effective. And that's really, we're looking for more and more of those kinds of projects. And we're really grateful that we've had these slew of projects, and we need a lot more in the pipeline as we go forward.
I guess the other thing I'd say from an industry standpoint, from our just workload, Rudy, we've been utility scale storage and the integration of battery storage into the overall marketplace is continuing to evolve. I think everyone's aware that the price point of and the energy density of battery technology is getting better. I think that's going to continue to. That's a story that's going to unfold and have broader impact, not only on the EV side, but utility scale side and the DER side. How that all plays together, to me, is not necessarily is something that's interesting.
Good point. Any other feedback from our project symposium presentations?